So here's a simulation that shows how that is possible, made by Joe Dwyer, Monte Carlo simulation. We have assumed a very strong electric field, a total potential of 110 million volts over a region that's 600 meters in horizontal extent and 150 meters in vertical extent. And the entire simulation starts with one seed electron, and it's accelerated upwards, and as it's accelerated, it interacts with other atoms and kicks off secondary electrons, which are also accelerated upwards and make this avalanche. And that's one process of multiplication. That's not enough to make the electrons and the gamma rays that we see in orbit. So you need this feedback process. Sometimes you'll get gamma rays made by Bremsstrahlung, but occasionally one of those gamma rays will backscatter and make a new seed electron, which will make another avalanche, which is another multiplication process. You'll also get, sometimes a gamma ray will pair produce and make an electron and a positron pair. And the electric field, of course, since the positron is the opposite sign, accelerate the positron in the opposite direction, where it can make another secondary and start a new avalanche there as another multiplication process. And in 10 microseconds, you get this incredible multiplication of secondary particles. These are all electrons, which then can make Bremsstrahlung and make gamma rays, which are what we observe in space with our detectors. So that's this runaway electron avalanche and relativistic feedback process. So now let's talk about some of the lightning observations. One of the main advantages of GBM for doing correlated observations with lightning is our timing accuracy. Previous experiments suffered from poor timing accuracy. Their onboard clocks drifted and had millisecond timing accuracy. With Fermi, we have microsecond timing accuracy by synchronization to global positioning system, and so we can correlate with lightning observations on the ground and line up our observations, which have led to some interesting results. These graphs show, these tick marks here, for example, are half millisecond, and the histograms here are showing the gamma ray observations on top of the data, the histograms and the curves. Here's a TGF that had two peaks, a single peak TGF, and a TGF that had two overlapping peaks. And then the vertical, two lines that are vertical are a lightning observation by the WLIN, Worldwide Lightning Location Network, which is very low frequency observations. The last talk mentioned a little bit. The advantage of the very low frequency observations is they can be seen at distances of up to almost 10,000 kilometers. So a network of a few dozen receivers can observe lightning worldwide, and by having multiple receivers observe the same discharge can locate them by a sort of triangulation process. So what's interesting here is we're showing that when we observe a lightning discharge in correlation with the TGF, they line up to tens of microsecond accuracy, which is a new result, and I think conclusively shows that the lightning discharge is associated, has some relationship with the TGF. Proves, I think, conclusively proves that lightning and TGFs are related, if anyone wasn't convinced already. But it raises a lot of questions. The arrows, of course, are pointing out, in several cases, we have the lightning leading the TGF, which would maybe naturally say, well, the lightning is causing the TGF, but we have this clear case here where the lightning is after both pulses of the TGF. So what is the causal relationship? It seems like there probably is not a causal relationship between the lightning processes that WLIN is able to observe in the VLF and the TGF, or at least it's very unclear since there's no set timing order. There's some other interesting aspects we get out of this, since Woolen is able to provide us with locations. We're finding out where these are. What these figures are showing you is the red X is the position directly underneath the spacecraft, and each green dot, you can't really see that they're separate dots, is a Woolen detected lightning discharge within plus or minus 10 seconds of the TGF. And then the blue square is the specific one that was observed in correlation with the TGF. And you see that in every case, the specific one that's in correlation is within 300 kilometers. That's this red circle. So the TGFs, the bright TGFs that we're detecting with GBM are always within 300 kilometers of the sub-spacecraft point, which is telling us what the beam angle is. The bright beam that we're able to detect has a size of 300 kilometers radius at 500 kilometers altitude, which is approximately 30 degrees opening angle. In the cases when we're not able to find a Woolen discharge in correlation with the TGF, which probably is just the detection efficiency of Woolen, there's always storms within that distance. Just clusters of lightning indicating that there's thunderstorm activity out there. So the picture gets a lot more complicated. These are some interesting observations that Steve Coomer has been doing with receivers in southern Florida, where he's able to observing the lower frequency domain and observing closer, so we're getting a different picture of the lightning observations within the 500 kilometer radius. And so what he's seeing is this particular TGF had multiple fast discharges. This particular discharge was observed with the NLDN network. It's, I think, pretty similar to the kind of discharge that Woolen would be able to see. But it actually had two fast discharges. There's this discharge and this one, which on the blow-up you see here. This is the kind of discharge that we're seeing with Woolen that's correlated with tens of microseconds to the TGF. But there's actually multiple discharges of that type associated with the TGF. And this has been seen before with observations by the Stanford group with their awesome network and RHISI TGFs. But with the low frequency receiver that he has, he's seeing this signal, and when he integrates it to determine the current associated with that signal, he finds this profile, which is very interesting because that profile tracks the gamma ray profile very closely. So that particular signal appears to be tracking the gamma ray time profile, and maybe that observation is actually seeing the actual current in the TGF itself, perhaps the relativistic electrons that make up the TGF. So we're maybe seeing that there are multiple processes involved, and I don't know which of them are actually causing the TGF. So to review, some of this is review, some of this is new. What do we know about TGFs? We know that they're associated with thunderstorms and lightning. We know that 1/3 of them are associated with Woolen, very low frequency radio discharges to tens of microseconds. It might be that the lack of 100% match rate is simply due to the detection efficiency of Woolen. Several observers have evidence that the lightning is intra-cloud IC lightning. Closer observations that I just showed you and show that there's multiple discharges of several types associated with TGFs. One of those types of processes that Steve Coomer has observed is a slower process that when you deduce its current profile has a similar time profile as the gamma ray profile, so it may in fact be the current of the relativistic electrons themselves. But I think what's very interesting, there's a